Quantum dots are semiconductor devices that tightly confine electrons or holes in all three spatial dimensions. They can be made via several possible routes including colloidal synthesis, plasma synthesis, or mechanical fabrication. The term quantum dot was coined by Mark Reed in 1988, however, they were first discovered in a glass matrix by Alexei Ekimov in 1981 and in colloidal solutions by Louis E. Bruce in 1985. The electronic properties of the quantum dots fall between those of bulk semiconductors and those of discrete molecules of comparable size, and optoelectronic properties such as band gap can be tuned as a function of particle size and shape for a given composition. For example, the photoluminescence of a QD can be manipulated to specific wavelengths by controlling particle diameter. Larger QDs emit longer wavelengths, resulting in emission colors such as orange or red. Smaller QDs emit shorter wavelengths, resulting in colors like blue and green. Although the specific colors and sizes vary depending on the exact composition of the QD. Because of the high tunability of properties, QDs are of interest in many research applications such as transistors, solar cells, LEDs, and diode lasers. For example, the ability of QDs to precisely convert and tune a spectrum makes them ideal for LCD displays. Previous LCD displays can waste energy converting red-green poor, blue-yellow-rich white light into a more balanced lighting. By using QDs, only the necessary colors for ideal images are contained in the screen. The result is a screen that is brighter, clearer, and more energy efficient. The first commercial application of quantum dots was the Sony XBRX900A series of flat-panel televisions released in 2013. QDs are also being researched as possible qubits for quantum computing. Beyond electronic applications, QDs are also being investigated in the medical field for medical imaging. Additionally, their small size allows for QDs to be suspended in solution, which leads to possible uses in inkjet printing and spin coating. These processing techniques result in less expensive and less time-consuming methods of semiconductor fabrication. Quantum confinement in semiconductors. In a semiconductor crystallite whose size is smaller than twice the size of its exciton Bohr radius, the excitons are squeezed, leading to quantum confinement. The energy levels can then be modeled using the particle-in-a-box model, in which the energy of different states is dependent on the length of the box. Much like the pitch of a string in a musical instrument is dependent on its length. Comparing the quantum dot's size to the Bohr radius of the electron and hole wave functions, three regimes can be defined. A strong confinement regime is defined as the quantum dot's radius being smaller than both electron and hole Bohr radius. Weak confinement is given when the quantum dot is larger than both. For semiconductors in which electron and hole masses are markedly different, an intermediate confinement regime exists, where the quantum dot's radius is larger than the Bohr radius of one, but not the other charge carrier. Band gap energy. The band gap can become larger in the strong confinement regime, where the size of the quantum dot is smaller than the exciton Bohr radius ab*, as the energy levels split up, where ab is the Bohr radius equals 0.053 nanometers, m is the mass, mu is the reduced mass, and epsilon r is the size-dependent dielectric constant. This results in the increase in the total emission energy and the emission at various wavelengths, which is precisely what happens in the Sun, where the quantum confinement effects are completely dominant and the energy levels split up to the degree that the energy spectrum is almost continuous, thus emitting white light. Confinement energy. The exciton entity can be modeled using the particle in the box. The electron and the hole can be seen as hydrogen in the Bohr model, with the hydrogen nucleus replaced by the hole of positive charge and negative electron mass. Then the energy levels of the exciton can be represented as the solution to the particle in a box at the ground level, with the mass replaced by the reduced mass. Thus, by varying the size of the quantum dot, the confinement energy of the exciton can be controlled. Bound exciton energy. There is Coulomb attraction between the negatively charged electron and the positively charged hole. The negative energy involved in the attraction is proportional to Rydberg's energy and inversely proportional to square of the size-dependent dielectric constant of the semiconductor. When the size of the semiconductor crystal is smaller than the exciton bore radius, the Coulomb interaction must be modified to fit the situation. Therefore, the sum of these energies can be represented as, where μ is the reduced mass, A is the radius, m is the free electron mass, mh is the whole mass, and epsilon r is the size-dependent dielectric constant. Although the above equations were derived using simplifying assumptions, the implications are clear. The energy of the quantum dots is dependent on their size due to the quantum confinement effects, which dominate below the critical size, leading to changes in the optical properties. This effective quantum confinement on the quantum dots has been experimentally verified and is a key feature of many emerging electronic structures. Besides confinement in all three dimensions, other quantum-confined semiconductors include quantum wires, which confine electrons or holes in two spatial dimensions and allow free propagation in the third; quantum wells, which confine electrons or holes in one dimension and allow free propagation in two dimensions. Production. There are several ways to confine excitons in semiconductors, resulting in different methods to produce quantum-confined semiconductor structures. In general, quantum wires, wells and dots are grown by advanced epitaxial techniques. Nanocrystals may be produced by gas phase, liquid phase and solid phase approaches. Colloidal synthesis. Colloidal semiconductor nanocrystals are synthesized from precursor compounds dissolved in solutions, much like traditional chemical processes. The synthesis of colloidal quantum dots is done by using precursors, organic surfactants, and solvents. Heating the solution at high temperature, the precursors decompose, forming monomers which then nucleate and generate nanocrystals. The temperature during the synthetic process is a critical factor in determining optimal conditions for the nanocrystal growth. It must be high enough to allow for rearrangement and annealing of atoms during the synthesis process, while being low enough to promote crystal growth. The concentration of monomers is another critical factor that has to be stringently controlled during nanocrystal growth. The growth process of nanocrystals can occur in two different regimes, focusing and defocusing. At high monomer concentrations, the critical size is relatively small, resulting in growth of nearly all particles. In this regime, smaller particles grow faster than large ones, resulting in focusing of the size distribution to yield nearly monodispersed particles. The size focusing is optimal when the monomer concentration is kept such that the average nanocrystal size present is always slightly larger than the critical size. Over time, the monomer concentration diminishes, the critical size becomes larger than the average size present, and the distribution defocuses. There are colloidal methods to produce many different semiconductors. Typical dots are made of binary compounds such as lead sulfide, lead selenide, cadmium selenide, cadmium sulfide, indium arsenide, and indium phosphide. Dots may also be made from ternary compounds such as cadmium selenide sulfide. These quantum dots can contain as few as 100 to 100,000 atoms within the quantum dot volume, with a diameter of 10 to 50 atoms. This corresponds to about 2 to 10 nanometers, and at 10 nanometers in diameter, nearly 3 million quantum dots could be lined up end-to-end and fit within the width of a human thumb. Large batches of quantum dots may be synthesized via colloidal synthesis. Due to this scalability and the convenience of benchtop conditions, colloidal synthetic methods are promising for commercial applications. It is acknowledged to be the least toxic of all the different forms of synthesis. Plasma synthesis. Plasma synthesis has evolved to be one of the most popular gas phase approaches for the production of quantum dots, especially those with covalent bonds. For example, silicon and germanium quantum dots have been synthesized by using non-thermal plasma. The size, shape, surface and composition of quantum dots can all be controlled in non-thermal plasma. Doping that seems quite challenging for quantum dots has also been realized in plasma synthesis. Quantum dots synthesized by plasma are usually in the form of powder, for which surface modification may be carried out. This can lead to excellent dispersion of quantum dots in either organic solvents or water. Fabrication self-assembled quantum dots are typically between 5 and 50 nanometers in size. Quantum dots defined by lithographically patterned gate electrodes, or by etching on two-dimensional electron gases in semiconductor heterostructures, can have lateral dimensions between 20 and 100 nanometers. Some quantum dots are small regions of one material, buried in another with a larger band gap. These can be so-called core shell structures, e.g., with CDSE in the core and ZNS in the shell, or from special forms of silica called ormacil. Quantum dots sometimes occur spontaneously in quantum well structures due to monolayer fluctuations in the well's thickness. Self-assembled quantum dots nucleate spontaneously under certain conditions during molecular beam epitaxy and metal-organic vapor phase epitaxy, when a material is grown on a substrate to which it is not lattice-matched. The resulting strain produces coherently strained islands on top of a two-dimensional wetting layer. This growth mode is known as Stransky-Krastinov growth. The islands can be subsequently buried to form the quantum dot. This fabrication method has potential for applications in quantum cryptography and quantum computation. The main limitations of this method are the cost of fabrication and the lack of control over positioning of individual dots. Individual quantum dots can be created from two-dimensional electron or hole gases present in remotely doped quantum wells or semiconductor heterostructures called lateral quantum dots. The sample surface is coated with a thin layer of resist. A lateral pattern is then defined in the resist by electron beam lithography. This pattern can then be transferred to the electron or hole gas by etching, or by depositing metal electrodes that allow the application of external voltages between the electron gas and the electrodes. Such quantum dots are mainly of interest for experiments and applications involving electron or hole transport, i.e., an electrical current. The energy spectrum of a quantum dot can be engineered by controlling the geometrical size, shape, and the strength of the confinement potential. Also, in contrast to atoms, it is relatively easy to connect quantum dots by tunnel barriers to conducting leads, which allows the application of the techniques of tunneling spectroscopy for their investigation. The quantum dot absorption features correspond to transitions between discrete, three-dimensional particle-in-a-box states of the electron and the hole, both confined to the same nanometer-size box. These discrete transitions are reminiscent of atomic spectra and have resulted in quantum dots also being called artificial atoms. Confinement in quantum dots can also arise from electrostatic potentials. CMOS technology can be employed to fabricate silicon quantum dots. Ultra-small CMOS transistors behave as single-electron quantum dots when operated at cryogenic temperature over a range of -269 degrees Celsius to about -258 degrees Celsius. The transistor displays Coulomb blockade due to progressive charging of electrons one by one. The number of electrons confined in the channel is driven by the gate voltage, starting from an occupation of 0 electrons, and it can be set to 1 or many. Viral assembly Li et al. Reported using genetically engineered M13 bacteriophage viruses to create quantum dot biocomposite structures. As a background to this work, it has previously been shown that genetically engineered viruses can recognize specific semiconductor surfaces through the method of selection by combinatorial phage display. Additionally, it is known that liquid crystalline structures of wild-type viruses are adjustable by controlling the solution concentrations. solution ionic strength, and the external magnetic field applied to the solutions. Consequently, the specific recognition properties of the virus can be used to organize inorganic nanocrystals, forming ordered arrays over the length scale defined by liquid crystal formation. Using this information, Li et al. Were able to create self-assembled, highly oriented, self-supporting films from a phage and ZNS precursor solution. This system allowed them to vary both the length of bacteriophage and the type of inorganic material through genetic modification and selection. Electrochemical assembly. Highly ordered arrays of quantum dots may also be self-assembled by electrochemical techniques. A template is created by causing an ionic reaction at an electrolyte metal interface, which results in the spontaneous assembly of nanostructures, including quantum dots, onto the metal, which is then used as a mask for laser etching these nanostructures on a chosen substrate. Bulk manufacture. Quantum dot manufacturing relies on a process called high-temperature Joule injection, which has been scaled by multiple companies for commercial applications that require large quantities of quantum dots. This is a reproducible production method that can be applied to a wide range of quantum dot sizes and compositions. The bonding in certain cadmium-free quantum dots, such as IIIV-based quantum dots, is more covalent than that in EV materials. Therefore, it is more difficult to separate nanoparticle nucleation and growth via a high-temperature Joule injection synthesis. An alternative method of quantum dot synthesis, the molecular seeding process, provides a reproducible route to the production of high-quality quantum dots in large volumes. The process utilizes identical molecules of a molecular cluster compound as the nucleation sites for nanoparticle growth, thus avoiding the need for a high-temperature injection step. Particle growth is maintained by the periodic addition of precursors at moderate temperatures until the desired particle size is reached. The molecular seeding process is not limited to the production of cadmium-free quantum dots. For example, the process can be used to synthesize kilogram batches of high-quality EV quantum dots in just a few hours. Another approach for the mass production of colloidal quantum dots can be seen in the transfer of the well-known hot injection methodology for the synthesis to a technical continuous flow system. The batch-to-batch variations arising from the needs during the mentioned methodology can be overcome by utilizing technical components for mixing and growth as well as transport and temperature adjustments. For the production of CDSE-based semiconductor nanoparticles, this method has been investigated and tuned to production amounts of kilogram per month. Since the use of technical components allows for easy interchange in regards of maximum throughput and size, it can be further enhanced to tens or even hundreds of kilograms. In 2011, a consortium of US and Dutch companies reported a milestone in high-volume quantum dot manufacturing by applying the traditional high-temperature Joule injection method to a flow system. On January 23, 2013, Dow entered into an exclusive licensing agreement with UK-based Nanoco for the use of their low-temperature molecular seeding method for bulk manufacture of cadmium-free quantum dots for electronic displays. And on September 24, 2014, Dow commenced work on the production facility in South Korea capable of producing sufficient quantum dots for millions of cadmium-free televisions and other devices, such as tablets. Mass production is due to commence in mid-2015. On the 24th of March 2015, Dow announced a partnership deal with LG Electronics to develop the use of cadmium-free quantum dots in displays. Heavy metal-free quantum dots. In many regions of the world, there is now a restriction or ban on the use of heavy metals in many household goods, which means that most cadmium-based quantum dots are unusable for consumer goods applications. For commercial viability, a range of restricted Heavy metal-free quantum dots has been developed showing bright emissions in the visible and near-infrared region of the spectrum and have similar optical properties to those of CDSE quantum dots. Among these systems are INP, ZNS and QANS, ZNS. For example, peptides are being researched as potential quantum dot material. Since peptides occur naturally in all organisms, such dots would likely be non-toxic and easily biodegraded.